Reliability-based analysis for failure modes of Mansard roof truss according to Euro Code 3. Abstract. This paper shows the results of the safety assessment of Mansard steel roof truss using the first-order reliability methods. 4 failure modes were considered in the studies: compression, bending, tension, as well as combined compression and bending failure modes. From the results obtained from the first-order reliability method, the safety index values range between 0.076 to 11.90 for the members, while the values for the joints range from 0.677 to 1.89. A careful study of the results shows that the safety index values decreased as the load ratio increased, and the safety index values at a particular load ratio are generally higher for the members than the joints. These results point to the fact that failure will be initialized at joint before progression to other members. Keywords: Eurocode, failure mode, form, reliability, safety index, stochastic model, truss. 1. Introduction. Steel trusses are normally designed to support imposed, wind and dead loads. Various types of steel trusses such as Mansard, storage, scissors, Fink, Howe, and others are opted for in designs. These trusses are selected based on design criteria before being constructed. These criteria include amongst others their usage, cost, span, 2, depth and so on. 1. Engineering design and analysis are based often on deterministic thinking, characterized in design calculations by the use of specified minimum material properties, specified load intensities, and by prescribed procedures for computing stresses and displacements. This has led to uncertainties, and conversely the application of prescribed safety factors in the analysis and design too. Because of these uncertainties, risk, the probability of structural failure from all possible causes, both from violation of predefined limit state and from other causes, is unavoidable. Though, uncertainties and their importance on structural safety and performance can be analyzed thoroughly only through the technique of probability. 3. Reliability-based design involves incorporating these uncertainties in current methods of design, thereby using probability methods to design at predefined safety levels. 4. 5. Looked at the reliability of structure by means of different target safety levels and probability distribution functions. The results showed that high target safety index makes it difficult to determine the safety factors such that the same safety level can be reached for different structures. In this work, a reliability-based analysis for failure modes of steel Mansard roof trusses to Euro Code 3.6 was carried out. The proposed design procedure considers the design of the Mansard roof truss using first-order reliability method, form, at target safety levels which the current codes of practice do not provide. 2. Limit state equations. The top chord is subjected to compression and bending. The bottom chord, tie member, and strut member are subjected to tension and compression. 2.1 Limit state equation due to compression. The failure mode due to compression is thus: G, X, equals permissible compression load applied compression load. The design buckling resistance of a compression member should be taken as, where NB, RD is the permissible compression load, is the reduction factor, A, is the section area, Ym1 is partial factor, and phi is the yield strength. For axial compression in members, the value of the appropriate non-dimensional slenderness should be determined from the relevant buckling curve according to Euro Code 3, where is value to determine the reduction factor, is imperfection factor, is non-dimensional slenderness. Therefore, where 0.1 is the slenderness value to determine the relative slenderness, E is Young's modulus, phi is the yield strength, is the coefficient depending on yield strength. From 2.6 Limit state equation for strut members. The failure mode due to strut members is thus: G, X, equals permissible compression load applied compression load. The design buckling resistance of a strut member should be taken as, where NB, RD is the permissible compression load, is the reduction factor, A is the section area, phi is the yield strength, Ym1 is the partial factor. For axial compression in members, the value of X, the appropriate non-dimensional slenderness, should be determined from the relevant buckling curve according to 35, where is the value to determine the reduction factor, is the imperfection factor, is the non-dimensional slenderness, where 0.1 is the slenderness value to determine the relative slenderness, E is the Young's modulus, phi is the yield strength, is the coefficient depending on yield strength. From equals, where NSD is the applied compression force, NB, RD is the permissible compression force. 3.0 Methodology. 3.1 First order reliability procedure. The reliability function of a given surroundings is the probability that the system survives all the actions exerted upon it by the surroundings. 7. The reliability is defined as the systematic calculations and prediction of the probability of limit state violation. 8. Probabilistic design is concerned with the probability that a structure will realize the functions assigned to it. If R is the strength capacity and S the loading effect, S, of a structural system which are random variables, the key objective of the reliability index of any component is to confirm that R is at no time surpassed by S. In practice, R and S are typically functions of different basic variables. 7. To examine the effect of the variables on the performance of a structural system, there are 5 elementary steps required to arrive at a value for the reliability index SS. The limit state equation is referred to as the performance or state function and expressed as. Graphically, the line G, 11, equals 0 represents the failure surface while G, 11, 0 represents the safe region and G, 11, 0 corresponds to the failure region as depicted in Fig. 1. Adopting a reduced, normally distributed variable expression for each variate. Finding an expression of the distance from the failure surface to the origin of the reduced variate space, let the distance in question be d. The distance d, from a point xi equals, x1, x2, xn, on the failure surface G, 11, equals 0 to the origin 11 space is also given as, where G** is the gradient vector at the most probable failure point, x1, x2, xn*. It is the value of SS which tells us of the safety of any given design under uncertainties in the decision variables. In equation 65, where basic variables are assumed to be normally distributed and uncorrelated, Taylor's expansion of G, x, about the mean yield quite precise approximations of SS. Though G, x, may contain non-normally distributed and frequently correlated variables, the accuracy of the estimates of SS be subject to heavily on the choice of the point of linearization. Form procedures resolve this problem by introducing suitable transformations altering all variables into uncorrelated normal variables, subsequently linearizing the emergent nonlinear function g, x, about a suitable point x*, selected through an optimization procedure, and hence a probability of failure is evaluated using standard normal integral. 4.0 Program Data Preparation. The Mansard truss shown in Fig. 2 was designed following EC3. The means, standard deviations as well as the statistical distributions of the basic design variables were prepared as shown in tables 1 to 5 by 7. 4.1 Parameters of stochastic model. The values of data used in the models are presented in tables 1, 2, 3, 4 and 5. Since the member forces are expressed in terms of the dead to live load ratio, the ratio was varied from 0.2 to 1.0 and necessary computation using form was carried out to determine the probability of failure PF and the corresponding safety index. This was done for the top chord members, bottom chord members, web members, as well as the joints. The results are tabulated in tables 6 and 7. From table 6 the beta values range 0.076 to 11.90 for the members, while the values for the joints in table 7 range from 0.677 to 1.89. A careful study of the results shows that the values decreases as the load ratio increases and the values at a particular load ratio are generally higher for the members than the joints. These results point to the fact that failure will be initialized at joint before progression to other members. A closer look at the results in Table 6 show that the safety levels, values, at all levels, exhibit the following trend. The strut members are the safest, having the highest safety level, tie members come next in succession, the bottom chord members are next with the top chord following. Failure in the members will be in progression, starting with the members having the least safety level. It should be borne in mind that since it is statically determinate structures, failure of any member or joint denotes truss failure. 8. 5.0 Conclusion and Recommendations. The reliability-based design of Eurocode 3 procedures for a Mansard roof truss system has been carried out with the aid of computer programs in the Fortran language. The form of analysis for the elements was carried using FORM57. From the results obtained for the first-order reliability method, the safety indices range between 0.076 to 11.90 for the members, while the values for the joints range from 0.677 to 1.89. Joint failure of a Mansard roof truss designed by Eurocode 3 will therefore be initiated before progressing to members under increased loading. It is recommended that Mansard roof trusses should be designed at a lower value of ratio dead to live loads. The design of the joints in Mansard steel roof trusses should be considered more seriously. The reliability-based design needs to be carried out considering other wind speed in different nations.